I'm sorry? Is it good? Yeah. Hey, thanks, guys. Welcome back. I realized that this is a great auditorium. You know, Rick Rashid has done something amazing for the world, great with the Microsoft research. I'm very excited to be able to give a talk in the Rashid auditorium. The other thing is Pittsburgh. I realized during the break that a lot of you are not from Pittsburgh, and you should go check it out. It's a city with a wonderful history. There is a TV series, which is sort of a little bit badly named, called The Men Who Made America or something like that. It's a somewhat dramatic title. But it talks about the post-Civil War in this country, all the way, sort of beginning of massive industrial wealth, and starts out with Vanderbilt and his railway empire, and slowly makes its way to Carnegie and the steel, and there's an interesting episode with Carnegie and Frick, who some of you may know from the Frick's collection in New York. And they had a lot of interesting developments happened in Pittsburgh and about that time. And if you had time,
I think we need to amplify you. Just keep on talking. I'll get you the other one. Just keep on talking. Ignore
Okay.
me.
Okay. So Frick and Carnegie, lots of interesting. The image looks darker than it used to be with the light, right? Yeah. Yeah. But I'll keep you guys entertained meanwhile. How many of you have seen any of Vermeer's paintings? Vermeer. I don't know how to say it. I'm sure there's a very nice Dutch way to say it. Okay. So this person, he made, I think, if I recall right, less than 30 paintings in his life, entire artistic life. Okay.
No, both on.
Both on.
Yeah. So one is for eternity and one is for now.
Very
All right. So whatever I say cannot be held against me in the future. Yeah, this person did less than 30 paintings, I think, in his professional career, and Frick won 3 of them. I think the remarkable percentage of ownership. If you go to the Frick collection in New York, you'll be able to see 3 of his paintings, from his paintings. Anyway, so Pittsburgh. We have 2 hours this afternoon to talk about data streams, and I'm going to spend a little bit of time talking about 2 technical results, very simple results, some of which some of you may have seen before. But these are nice little primitives to have. One is called count-min sketch or sketch, and the other is L0 sample. And you'll see that there are a bunch of applications for these things. That'll be the first part of the lecture. And then I want to spend a lot more time on half a dozen problems that I like to formulate. And many of them are problems that I don't completely understand, and it'll be nice to formulate them, and they're good basis for doing research. And some of them are on the slide, and others I'll just make them up as I go along. And the lunch was very useful. I sort of had a good idea of some of the problems I might want to discuss here, the lunch. So I want to start with this count-min sketch. Okay. As I said, as an algorithms person, you're constantly asking, what's the simplest problem that you want, that's sort of hard, that you want to solve, that helps you solve a whole bunch of other problems. Okay? In databases, for instance, if you work with any database, there's something called index query. Okay? It's very important. All databases are more or less optimized to run index query. Right? Index query says you can take a collection of data, put it into something like a B tree, some variation of B tree, and then you could ask queries about a particular record there. You could ask, what's this person's grade? What's this person's salary? Or, so those are called what I call point queries. Okay? So once you optimize for index queries, then you can do a lot of things with it. You can do range queries, and you can build up more complicated queries on top of it. And to some extent, I think of algorithms the same way. So for me, one of the most basic problems is this indexing problem. And in our context, where we work with small space, here is how the problem would look. Okay? You have some sort of an array of size n, but n is very, very large. So you just keep this in your mind. You don't actually want to materialize this array. Okay? And you're going to see updates to this array, either increments or decrements. Okay? For example, this array could be the number of bytes sent by an IP address. Okay? So 1 through n stands for the source IP address, and fi is the number of bytes sent by the IP address I. Okay? So when you see a new packet, you know the source IP address, and you know that the packet consists of some number of bytes, so you can increment that many bytes to the correct location of the array. Okay? So this array in your mind can be used to track different signals in the underlying data that you see. Right? You might define one array for the source IP address, one for the destination IP address, and one for the port numbers, and one for different protocols, one for all picture updates in Facebook or whatever. Right? Or you can have, even this array can be indexed by the users. You could say the number of times the user is logged in, or the number of updates by the user. So fi could stand for any one of the signals that we want to associate with some entity called I in that application. But in an abstract sense, each transaction is an update, either an increment or a decrement. Okay? And let's assume for now that at no point do the decrements get the array entity to be negative. So if you keep adding something to it and subtracting, and at no point does fi become less than 0. Okay, they're either 0 or above 0. Okay, just a technical reason it makes it easier to do the arguments. Okay. Certainly, if you keep track of the number of bytes, then you see only increments, you don't see decrements, and it will always be non-negative. Okay. And you could keep track of something like number of active connections that IP address is involved in, and that would mean increments and decrements. When a connection is terminated, you can decrement the number of active connections. And you still want when you're still counting some activity like that, fi is always non-negative. You don't get to be, you don't get to have negative connections. Okay. So that's the context, and you want to. That's a transaction. So the query is, as you keep updating this array, once in a while you get asked query, what is fi? Okay. What is f1 and what is f100, whatever. Okay. And you would answer the query. And by now you know that you can answer the query if you had a B tree or a hash table. You can just answer the query exactly. But we won't be allowed to have the space proportional to n, the size of the array. We're going to have much less space to solve this problem. Okay? So there are a bunch of ways to solve this problem. They use these small space data structures, or what we call sketches. You may have heard of them already. And I'm going to tell you one such sketch. There are several sketches out there. Okay? This is called a countment sketch, and what it does is, rather than maintaining an array f1 through fn, it maintains a smaller array, and it maintains several copies of a smaller array, several versions of a small array. Okay? So each small array corresponds to a hash function. So what you do is you have 1 through n, and each of the items get hashed to a smaller domain, smaller range, and that will correspond to one of the rows in this picture. Okay? So rather than track f1 through fn, you track this cm1 to cm some number here. Okay? And you do that with by mapping all the items using a single hash function. And now you do the same thing with a bunch of hash functions. So those are the different rows. So each row stands for a different hash function, and the bucket or the counters in each row corresponds to taking many of the elements from the original domain, original universe, and mapping them down to this range. Okay? So this data structure almost always is a case that when you use very little space, you cannot answer queries exactly. So you have to be approximate. And in this case, we are going to use probabilistic methods, so you're not going to always succeed as well. You're going to have some failure of probability. Okay? So there's going to be approximation and failure of probability. And the approximation is going to be given by a factor epsilon. And you'll see its effect in a minute. And likewise, and the probability of success is going to be given by some parameter delta. Okay? And these two parameters are going to tell you how big these counters are going to be, okay, these tables of counters. So the number of counters in a row is like 1 over epsilon. Okay? It's E over epsilon. It's 1 over epsilon. So the accuracy of our algorithm is going to depend on the number of counters in a row. Okay? Yeah. So it's a function of 1 over epsilon. And the number of rows is going to be log 1 over delta. And as I said, delta determines the probability of success or failure. So the number of rows are going to govern the likelihood that you're going to get good answers. Okay? So those are the two parameters. And notice that n, which is the size of the original array, is not in this picture here. Okay? So you're taking a very large array and mapping it down to a bunch of small number of counters and doing it a small number of times. And this is the way you represent f. So now what happens is when you see an increment or decrement to a particular location I in the original array, then here is an increment to the location I. So you compute a hash of the location I, and it's going to map to some counter here, and you do the increment in that counter. Do the same thing with the second row with a different hash function, the second hash function, third row with a third hash function, and so on. So each row has a different hash function, and each time you see an increment or a decrement, you hash that item that you want to increment or decrement by each of the hash functions, and that will map the item to one of the counters or buckets, and do the update there with increment or decrement. Okay? That's what we do with the transaction of updates. And then the question is, how would you respond to a query that says, what is fi? Okay. When the query arrives, what is fi, you do something very similar to update. You compute the hash, where does I hash into using the first hash function, the second hash function, third, and so on. And each of them will give you a counter value. We're going to return the minimum of those counter values as our answer for fi. Okay. So it's a good idea to sort of contrast this with what would you have done if you had a hash table of full size, right? If you had a hash table of size n, when you had an increment or decrement, you will hash I to an appropriate location in the hash table, and then you'll increment or decrement in that counter. And then when the query arrives, what is fi, you'll hash I and go to that counter and just return the value there. Okay? That's what you would do. We're doing something similar in each row, except that our hash function takes n and maps it to something small. So many items in the original array would map onto one counter. And when a query comes for what is fi, like in a hash table, we look at where I hashes to and take the counter value. But we don't return it directly. We return the minimum of all the counter values we get with different rows. Okay? So this is like doing a hash table with multiple hash functions. And since these hash functions map the universe to something very small, there will be a lot of collisions. And so you're going to return an answer. Each time you look up I, you're going to get different numbers from the different counters corresponding to different hash functions. So you have to figure out what number to return. And this method says return the minimum number. Okay? And so just for precise purposes, you can see in the slide how we do this. For each update fi, for each of the hash functions 1 to log 1 over delta, you hash I using the hash function j, and update that counter cm in the jth row. Okay? And do this for each one of the rows j from 1 to log 1 over delta. Okay? So you see as many hash functions, and the number of counters would only come from the definition of hash function. Okay? And when you want to estimate fi, you hash I again is using each of the hash functions and return the minimum, smallest value of the counters. I found it easier to understand this method if you just think about one hash function. So there's a single row. And if you think about it, then it's doing essentially what a hash table would do. Okay? And having multiple hash functions, you'll notice, will serve to make sure that our error probability goes down. And when you do that, you're going to have multiple estimates for the same fi. So you had to figure out a way to determine one outcome from multiple estimates, and we do the minimum estimator here. Okay, so that's a way to understand the sketch. So what can we show about this estimate? So think about a single row. And if you used only one hash function, and if you want to estimate fi, you'll go to where I hashes into the bucket, and you return that number. Well, anytime I got incremented or decremented, it always happened on that counter. So whatever you return should be at least what the correct value of fi would be. Okay? For example, if fi was 10 and it was incremented 10 times, all the increments would have happened in the counter where I hashed onto. Okay? So if you return that counter, the value you return should be at least fi. Okay? So you return f tilde I, so it has to be at least fi because all the transactions you did on I are done on the counter where I hashed onto. Okay? The problem is a lot of other items also hashed onto the same counter. So they also contributed to this counter that you return. And the question is, how bad is that? Okay. So this is array of size n, and you mapped it to a small set of counters, and you're looking at the fact that I mapped onto this counter, and you want to return that as an answer. So anytime you do the transactions here, do the transactions here as well. So we're cool on that side. But we also updated this counter every time some of the other items mapped onto this place. Okay. So, and they all contribute to the counter that you're returning. Okay. And you need to figure, and they induce an error, and you want to figure out how bad that error could be. Okay. So if you look at this value, so this is f tilde I. Okay. We are now working with only a single hash function. Okay. Certainly, all the increments here came to this counter. So that is, when we return this, what we return should be fi plus the contribution of all the other items. Okay. Now, how do you estimate the contribution of all the other items? Roughly, if you think about it, think of all the other guys. Okay. How would they contribute to this bucket? Only if they hashed onto this bucket. And we're using a hash function, let's say, that uniformly spreads out all the items. So if you have k of these counters here, then roughly you expect that 1 over k of the contribution of all the other items will go to this bucket. Okay? So there are roughly k buckets, and you're throwing all the items randomly into this k buckets. If everything goes well, 1 over k of the items would end up falling into this bucket. Okay? So roughly you expect that of all the other guys involved, if you sum up all the total contribution, 1 over k of those contributions should go to this, they will end up in this counter. Okay? So you roughly expect that your estimate that you give should be the right value plus the contribution of all the other guys that contributes to it. Okay? This is what you expect to see happen. Okay? You can make this formal. You can say what's the linearity of expectation, what's the expected value. Since we're doing this randomly, you have to write down the expected value of the contribution to each bucket from all the other items, but that's what you expect to see happen. Okay? And so what's the number of buckets, though? The number of buckets is like 1 over epsilon. Okay? So if you rewrite this, it'll be something like epsilon times this. Okay? And this is what I returned there as our upper bound. Okay? So notice that this is a statement that I expect this to happen. This doesn't tell you that it happens with a high probability. Okay? Because I wrote this for a single hash function. And I looked at what's the expected contribution of all the other items to my overestimate. So the expected value of what I return would be expected value of this plus the other guy's contribution, so epsilon times the others. Right? Now this isn't quite proof the claim there that says with probability at least 1 minus delta, this will be true. Okay? In order to prove that, you do a little bit more technical work. Okay? So let's go through this. Okay? Let's look at this random variable xij to be the expected contribution of fj to the bucket that contains the item I that you're looking for any of the hash functions, right? So the expected value of the contribution of others to this, the expected is sum of all the guys divided by the number of buckets, which is what I have there. Okay? So rather than 1 over epsilon, I'm using e over epsilon for precise calculations. Okay? Then you want to ask, what's the probability that the estimate that we have is greater than what we claim to be? Epsilon over e. Okay? This is our expected estimate. Our estimate will be this in expectation. We're asking, so what's the probability that this will be greater than, in fact, let's say, epsilon? Okay. For this to be greater than epsilon, greater than this right term, okay. We know that f tilde is fi plus sum of all these fj's epsilon over E. Okay. And we want this to be greater than fi plus epsilon times summation of fj. Okay. So the claim there is that our estimate is at most fi plus epsilon times sum of all other items. And I have computed this and argued this already. So I start with this line here. I'm trying to say, what's the probability that that upper bound would not be respected? The probability that this tilde is greater than f plus epsilon times the rest of them is, I know what this f tilde is. F tilde is fi plus the number of buckets, the total contribution of others divided by number of buckets, which is this term. Okay. The difference between this term and this term is that there's an 1 over e term here. Okay. What's the probability that this is greater than this? Okay. I'm sorry, this is, let me rewrite this as xij. Okay. And that's the same thing as probability that this variable is greater than, you can cancel out these terms, then E times expected value of xij. Okay. Because we already argued that expected value of xij is epsilon over E times sum of the rest of the terms. Okay. So this gets it into a form in which we can, if you've done this kind of stuff before, you can easily recognize what it's saying, right? It's saying, what's the probability that some variable, random variable, is greater than some constant times expectation, its expectation. Okay. But you want to do this for all hash functions j. Okay. So you're returning the minimum value over all the hash functions. The only way that the minimum value will be bigger than our estimate, our claim there is if the estimate from each one of the hash functions is larger than this number. Okay. That means that for each one of the hash functions, it should be true that the contribution of others to the bucket is greater than constant times the expected value. Okay. So this is very critical because this for all rows, this has to be true, comes from the fact that we use minimum estimator. Okay. Now there's a very nice simple Markov inequality that says this is at most 1 over e. Okay. And you want this to be true for every one of the hash functions, so that gets raised to the number of hash functions, and that will give you delta or 1 minus, or will be delta. Okay. So what that will show is that the probability that our estimate estimates that quantity, exceeds that quantity, is at most delta, which means with probability at least 1 minus delta, our estimate would be at most that quantity up there. Okay. So just to go over the argument again, we return an estimate, and we easily argued that the estimate is at least the correct value of I. Okay? But then there's a contribution from other guys, and you say, well, I have a claim up there, and you ask, what is the probability that our estimate will not meet that upper bound we have there? Okay? Well, it wouldn't meet that upper bound if the estimate, the correct value plus the contribution of all the other guys together exceeds that upper bound there. For it to exceed that upper bound, this is the correct value plus the contribution of others should exceed this upper bound I have there. So you can cancel out these fi terms, and it goes down to the contribution of others to this counter should exceed this term. This is nothing but a constant times its expected value. Okay. So that's what you have here. And then you argue that this can happen for a single hash function, but the probability that it happens for all hash functions is very small. Okay. You're going to be wrong only if it happens for all the hash functions because we return the minimum value. Okay. So the probability that it goes wrong for one of the hash functions is 1 over e. The probability that it goes for all the hash functions is that raised to the power number of hash functions. And that gives you an upper bound on the probability of error. Okay. So which means that with probability at least 1 minus delta, your estimate would have the property that I listed above. As proofs go, this is probably one of the simplest proofs you're going to see. Okay. At some point, I think I had even a pictorial proof of this claim. Okay. It's a very simple argument that uses just this inequality, this property that what's the probability that random variable is larger than its expectation by some constant is a Markov inequality. It's a very simple inequality in probability, and that's all you need to make this argument. Okay. So just to summarize, if you use this data structure, we have an estimate that's at least a correct value, and at most a correct value plus epsilon times sum of all the other values there. Okay. Now, why would this claim be interesting? Okay. In fact, when we worked on this result, which was more than 10 years ago, when we were trying to generate results of this type, it was not even clear to us that this was an interesting claim. This looked like some sort of technical calculation that we did. Okay. We knew that it was not giving us anything like the result we wanted. The result we want would be to say you have a large array of f1 through n, and you have a small sketch such that if anybody asks for any fi, we'll give you a constant multiplier or 1 plus epsilon approximation to the value, right? For every one of the i's, we should be able to give a good approximation. Okay? And we weren't getting that here, right? Because if you're using that to estimate an array, a large array, where fi happened to be 1 or 2, while there was some very, very large, think of an array f where some items are very small and some items are very large. Okay? And you're trying to estimate this I, this fi. Well, this could be like 1 or 0 or 2, while here you could have a million large sized elements sitting out here, right? And you don't get an estimate that says if it is 2, I get within a factor 2 of that, factor 10 of that, factor log of that. You don't get any error approximation of the type. You say that your estimate for this will depend on sum of all the other guys. Okay? That seems like a pretty bad estimate when you look at it. And in fact, at the beginning, it was not clear this is even an interesting estimate to have. So quite honestly, up until this paper, people were not really looking at point queries. They were looking at norms, and norms are easy to estimate to relative error. If a norm is small, you can get a 1 plus epsilon. You can always get a 1 plus epsilon or constant factor approximation. So if it's small or large, you always get a multiplier of an approximation. Well, here we have a situation where we don't really get a multiplicative approximation. It wasn't clear it's useful. Okay? But it has other interesting properties that it uses very little space, right? Space is like 1 over epsilon log 1 over delta, where you could have epsilon to be like 1 in 1,000, probability of success like 1 in 8. So it ends up using something like log 1 over, so something like 3,000 bytes. Okay? So you could have a very, very large array, 2 raised to the power 32, 2 raised to the power 64, and you're using a few thousand bytes to track this array, so it looked like a very good space usage. And the time is also very nice, because every time you had to update or ask a query, you just compute one number for each one of the rows. And the number of rows is the number of hash functions, which is like 3, 4, or 5 hash functions. So it seems very fast to update and to query. Okay? So that was a good part. And so we were looking at this estimate and saying, so what can you do with this? Right? So at the time, it was very early on in the theory of data streams. We were slowly developing the idea that with the small space, what you can do is you can't really follow a lot of little items. You can only follow the big items. You can only follow either very large volumes or very large changes in volumes. You can't really follow every one of the small updates that's going on in the stream. And we're just developing the intuition, and we didn't know how to capture that intuition. And this theorem sort of helps us do that to some extent. Right? So imagine you have this large array I talked about, and you're trying to estimate the small elements. We get a very bad estimate, because we're going to get an estimate which is the correct number plus epsilon times sum of all of these big guys. Okay? That's a big number there. Okay? And that's not so good. Okay? On the other hand, if you're trying to estimate this big guy, okay, we do a very good job. Okay? So if the big guy is like 1/100th of the total volume of all the f's, then if I set epsilon to be 1 in 1,000, then I got a really good estimate, like fi plus 1,000th of the rest of the guys. Okay? So that gets to be a very accurate estimate of something. Okay? So to the extent that fi is large, some total fj divided by something, like 100, like 500, 200, whatever, then I can set epsilon to be like 1 in 1,000, and I'll get an extremely good estimate for those large numbers. Okay? So this theorem tells us that we have a very large array. There are a lot of little guys, and you can't do anything about them. But if you focus the attention on the few 100 big guys, the guys who are really very big, then this term will be useful in estimating those guys very well. That's an intuition. I mean, the formal claim is there. Okay. So that was pretty useful for us. From there on, a lot of data stream work. We know things that we could do and things we cannot do. We know that we can estimate big signals, whether big changes, big relative changes, big volume movers, what the network people call elephant flows. But we can't really keep track of all the other little guys. Okay. So that was a good insight for us. Okay. Um, the other thing about theoretical computer scientists and algorithms people that I like is that when I'm in a company of people, even technically trained people, physicists, mathematicians, whatever, okay, or you're trying to sort of discuss your area of research, and so sometimes you can think of. I found that a lot of people find it easy to think of algorithms. If you tell them, well, I have 2 matches, I have 1 match, I have a rope, I want to burn it, 45 minutes, yada, yada, yada. They'll say, well, I know how I'm going to do it. I'm going to cut the rope. I'm going to, So a lot of people find it easy not easy, natural to think of algorithms of what they would do. Okay? It's very difficult for them to say that no matter what somebody else does, okay, prove to me that something is not possible. Sort of a lower bound or impossible results are often hard for people who are not mathematically trained, who are not actually trained to think this way. Okay? So, I'm sorry, there was a question there.
Is there a difference between the smaller values and the bigger values? Huge difference between the two? Unless there is a huge difference between the two, you cannot say that it is estimating the bigger values right and the smaller values.
Is there a big difference between the big guys and small guys?
The numerical difference between the, let's say, f of say 10 or something is high value, and f of 1 is also giving high value, but it's relatively very sparse. Is there a difference between the quantity of the two so that you can say, okay, this estimate is doing good for the higher values and these are all the small values?
Okay, good. So let me rephrase your question the following way. The claim is that if there is an I such that fi is large with respect to sum of all the other guys, then you get a good estimate. So you don't have to look for a weaker claim, sort of more simpler claim like if these 2 items are such that one is larger than the other, would you get a good estimate? We don't have such claims. You're saying that if an item is absolutely large with respect to everybody else put together, then you get a good estimate. So it's possible that 2 items, so one is a million, other is 1. And so a billion is larger than 1, and you think you'll get a good estimate for a million. That's not the case. You'll get a good estimate for the million if it turned out that all the other items are much smaller than the million. Okay? So that's really what the claim says. So they were saying many people find it natural, and many people are smart in thinking about sort of ways for doing things. It's difficult if you ask them to argue that no matter how smart somebody is, you cannot do something. The lower bounds or impossible results are harder. Okay? So what we want to do is to prove something of the type here that says, well, here is one algorithm. What makes us think that somebody couldn't be smart enough and design an algorithm which uses space even square root of this, much smaller than this? We use 3,000 bytes, but maybe they can get away with something like 10 times square root of 3 bytes. So you don't know, and you could say, well, no, I don't know how to use space less than this, but that doesn't mean somebody else cannot think of a better algorithm, right? So you had to prove something about lower bound, and that's often hard for a lot of people who are not trained in computer science like us, or theoretical computer. Okay. So I just want to go through one of the arguments, a simplest argument of this type, so that you know how these things work in this case. Okay. So we want to argue that you cannot improve the sketch. And the way we're going to argue that is by using a this works. Result in a communication game. Okay. So we have 2 parties, Alice and Bob. Okay. And Alice has a n-bit string. Okay. This is a bit string. Okay. And Bob has a particular index in mind. Okay. And the game they play is, so Alice has his n bits, and Bob has only a particular number in mind, and that's some 10 or 100 or some index, the bit that he wants to understand, Bob wants to know. The way the game is set up, Alice has to go first and say something to Bob, and then Bob has to be able to compute his answer. And the question is, what's the smallest number of bits that you think Alice has to transmit to Bob? Okay. So think of things from Alice's point of view. If she knew which bit Bob is interested in, she can just send that bit over. But she doesn't know that. Bob could be interested in any one of the bits. And so she can't ask Bob, what bit are you interested in? She has to just speak once and go away, write something in an envelope, drop it and go away. And then Bob has to be able to figure out the right bit, the bit that he's interested in. Okay. So you can ask yourself, how many bits do you think Alice has to send over? Okay. Intuitively, it seems obvious that all Alice can do is send all the bits over. Right? So she holds back one of the bits. She has no idea that Bob does not want that bit. Right? So intuitively, that's the case. It requires a moment of proof to prove it is against randomized strategies and so on. But we're going to take that for granted that if you look at that problem, where Alice has n bits, and Bob wants to know some particular bit, but Alice does not know which one, then the number of bits that Alice has to communicate to Bob is at least n. Okay? That seems intuitive, and I'll use that. Okay? And so we'll assume that you need at least n bits to communicate. Okay? So I'm assuming that most of you have seen big O's and omegas, right? Okay. It's a reasonable assumption. I think one of my claims to fame that I want to have is that Berkeley has a Simon Center on theory of computing. And they ran a special year focus on big data. And I gave them a logo for it. Okay. And the logo was something like this. And I was pretty excited about it. Yeah. And just in case anybody's paying attention to that, I used my Surface Pro to design this logo. Anyway, I think the class, it's about 2:30. Class needs a joke. So I think I said this to some people before that I have a collection of theoretical computer scientist jokes. Okay. And some of them are nice, some of them are, I think one of the most exciting things that happened was in my blog. I once I told the theoretical computer scientists that we were running the game in which you could take names of the movies and convert them into theoretical computer science version of them. Right? And there are lots of name titles of movies, well-known movies that you have a computer science version of. Right? There is the this is one of the movie names. Okay. So there are, I'll search for it. I think Amit at Dartmouth was very, very good about this. We spent a workshop in Germany and in Dockstuhl, and we spent much of the evening coming up with names of movies that there were a theoretical computer science version of them. Okay. So anyway, there are lots of good theoretical computer science jokes with big O's and omegas. So we start with this index problem, and let's assume that's true, that Alice has to communicate a lot of bits for Bob to solve this problem. Then we're going to show that our problem is hard. Our count-min sketch problem is at least as hard as this. That if you wanted to improve our count-min sketch bounds, then you'll end up improving the index problem, which is not possible, which is a nice proof. Okay. So the way we're going to do it is by reducing one to another, from reducing the problems. Okay. So we start with saying, well, if there is a large array F, could there be a sketch of very little space that will be able to answer an index query and will use space less than what count-min sketch does? Okay, this is our question, right? So what we're going to do is to think of it as saying, well, I'll give you a way to solve this problem using the index problem. Okay, that'll be the reduction, and that'll give us our argument we want. Okay, so we're going to construct an array for Alice from the array that we have for the count-min sketch. So we're asking, could there be a smart algorithm for this for the index problem, for the problem of estimating FIs very well, which uses very little space? Well, we're saying, well, if you're trying to solve this problem, just think of the corresponding problem for Alice and Bob, where there is a bit string. Yeah, so I'm sorry. The way we would think about it would be the way we'll solve the bit string problem for Alice and Bob is, well, Alice has this bit string. Think of that as an array, f1 through fn, where if this bit, ith bit was a 1, then we're going to think about this f of I here as a 2. Okay? So we're giving a method for Alice and Bob to interact, and they're trying to solve this communication problem for indexing. So we take their input, and we construct a problem for our problem. Right? And whenever if the ith bit is 1, we think of it as a 2 in our array. And if the ith bit is if it's a 0, then we think of it as a 0 here, but we add 2 to the 0th location here. Okay? So whenever I is 1, fi becomes 2. Whenever I is 0, we set fi to 0, but we add 2 to a new location called f0. Okay? Now imagine that this array is of size, let's say this array is of size 1 over 2 epsilon. Okay? There's a reason why we picked this way. Then after you've done this transformation, the size of this, if you sum up all the fj's, 0 to 1 over 2 epsilon, that should be equal to 1 over epsilon. Because for each entry there, either it is a 0, each bit array has either 0 or 1. Each of them contribute a 2 to the f array, either at the ith location or the 0th location. So if you sum up all of them, it's 2 times 2, 1 over 2 epsilon, that becomes 1 over epsilon. That's the size of all of them. Okay. And that's this observation. Okay. So now, let's see, what does it mean to estimate fi? Right? So we're given a procedure for Alice and Bob to communicate so that ith item can be indexed by reducing it to this problem. And now we're asking, if there was an estimate for this problem that we have, that's a counting sketch problem, if we want to estimate this with this accuracy, then it will have the property that if there was a 0 here, then fi will become a 0, and its estimate, according to our claim, would be between 0 and epsilon times the total size of the array. The total size of the array is 1 over epsilon, so it should be between 0 and 1. Okay? If fi was a 1, then if ii was a 1, then the corresponding element in the array will be 2, and our claim of estimate will be between 2 and 3. Okay? Just by plugging in the numbers here. Okay? So what that means is, if Alice and Bob are trying to solve this problem, then if we do this transformation of this array and give it to anybody who claims very smartly that they can solve this count-min sketch problem, then they're going to give you this guarantee. That's what count-min sketch does. And if they give that guarantee, then if I estimate any one of the fi's, if it is between 0 and 1, then it has to be the original bit was a 0. And if it is between 2 and 3, then we know the original bit was a 1. Which means that this smart algorithm that somebody has developed for solving this count-min sketch problem would end up solving the indexing problem. Okay? But we know that that's not possible. We know that that would require at least n bits, which means that anybody who claims to have such a solution requires number of bits at least proportional to the size of this array that we began with, and that's size of 1 over epsilon. Okay? So in other words, any method that somebody claims gives you this kind of guarantee on the accuracy of estimate has to at least use 1 over epsilon space, which is what count-min sketch does. So you cannot improve the epsilon factor. Okay? That's the argument. Okay? So just to unpack it, sort of repack it a little bit, what we're showing is that there's a very natural communication problem where you need at least n bits to be communicated. Now we are transforming that problem into our count-min sketch type problem and saying, if anyone guaranteed that they can give a count-min sketch type guarantee on the estimate, then they have to use at least 1 over epsilon space. Okay? They can't use square root of 1 over epsilon. Okay? Something smaller. Okay? So that's a good argument to have. Okay? It's a very, very simple argument. Of all the kind of open arguments, this is it's a trivial argument almost. Okay? But it sort of tells you how you might want to seek lower bounds and upper bounds when you do a calculation. Right? When you do your one, you might have some variation of the problem. Then it's easy to start with a nice index problem and do the reduction. Okay? You may want to see some of the recent work of David Woodruff, who's use a similar kind of reductions with much more sophisticated, more complicated, with many different types of indexing problems, asymmetric indexing problems, and so on. Okay? So if you can come up with the right communication problem to begin with, which has a nice lower bound, then you can use that to prove lower bounds for lots of other streaming problems. So this is something I tell a lot of people who are not in the algorithms community, that especially in machine learning, there are a lot of new techniques that are already known to machine learning people. They know something called dimensionality reduction, that you can take a set of points in a very large space and map it down to points in a small space. Okay? And you can do it using projections, which is to take some random projections, take some vectors, and do sort of a geometric projection. Okay? So these are algorithms or techniques that are known to people. But what I want to point out is that not all projections are the same, not all dimensional reduction techniques are the same. This method works because it does it in a particular way. It's a particular projection, a particular dimensional reduction, and that's the way it works. So just as a contrast, prior to this work, nearly all the other methods in this area used projections which are L2 preserving projections that were nearly all the prior work. So if you had to project L2 distances between points, then you need at least 1 over epsilon square space. And we're using much less space on that because we are not actually preserving all the pairwise distances. Okay. And well, this is a hashing algorithm, and as soon as you say hashing, everybody thinks that they know hashing, right? They know hashing. They do hashing. Not all hashing algorithms are the same. In order to get this proof, you have to use a particular type of hash function, so the proof will go through. Okay. And the other thing I hear from statisticians in particular is that, well, you know what, this is not very exciting. We know how to estimate things. We will sample. Okay? So I have spent a lot of time trying to figure out how to defend my work before statisticians. Okay? So this has always been an interesting exercise. And computer scientists are constantly in the place of having to defend our work in front of physicists, mathematicians, yada, yada, yada. You know. One of my favorite story of Michael Rabin is that, I don't know how many of you, I hope all of you know Michael Rabin's work. Okay, he's the one primarily who started the whole area of randomized algorithms. Okay. And early on in the 70s, if you saw the randomized algorithms, they were extremely simple algorithms. They would like take some random seeds and then test out some factoring. It looked very easy. And they were solving complicated problems, closest pairs problems, random primality testing. Pretty complicated problems that Michael was solving was using very simple algorithms. And so the story that he told me was that once he was invited to give a talk, I don't know, International Congress of Mathematicians or something, and he starts giving the talk, and there's a mathematician in the audience or somebody in the audience who says, "But this is so simple." And Michael explains his algorithm, and he says, "It's so simple." Okay. And I would not know how to respond to something like that, but apparently Michael's response was, "Well, thank you. That's exactly what I wanted." That's amazing. It's incredible. So we're constantly in the place of having to defend ourselves in front of other people. And one of the things I often found is that in a given approximation of an estimated quantity, and statisticians would think, well, they have an enormous history of approximations and estimations, so they must know about it, and particularly they must be sampling way of solving this problem. And this is an example I created just to show that that kind of argument wouldn't work for us. Okay? So the problem with sampling is that it doesn't sort of deal well with the world where items get removed. So imagine that you have somebody who inserts or plus ones 1 million items in a very large array. You have a 1 million items collected so far, and then you're allowed to have only a small space memory. So say you keep a sample, 100 items, right? Or some information about sufficient statistics, some distribution of these points, but 100 bytes. But you have 1 million items. You can't keep track of all of them, right? And then what happens is somebody removes all but 4 of the items. Okay. So they say, well, I insert 1 million names, and then I remove everybody except Alex and Zico and Muthu. Okay. Well, when you keep a sample, you don't know whose names are going to get removed, and you can't keep track of all the names. So you're going to keep track of some names. But the chances are you're not going to succeed in keeping track of the 4 names that somebody's going to remove in the future adversarially, right? So if you kept a sample and somebody removed this, the only way you can update the sample or refresh the sample is to go back to the data and resample, right? If you say, well, I'm going to keep track of 3 names, Michael Jordan, John Lafferty, whatever, and then you keep a sample, and then somebody says, remove Michael, remove John. I have nothing in my sample. Okay. How do we get right size? If you had a right size sample, you're going to get estimate, but you had to now rebuild the sample. You can go back and say, well, give me somebody else from the original set that was not Michael or John. Okay. But that would mean you have to go back and look at the history. That means you have to store all the items in the history, which we don't have time to do. Okay? So samples don't work that well when you're trying to delete items. But on the other hand, the sketches work well, okay? Because they are, if I take the CM sketch of this part of F array and another F array or another G array of same dimensions, if you add them or subtract them, it has the same. It's going to look the same. You can do it just by taking the counters of CM sketch and just doing all the operations. So if you have a sketch of the million items and somebody removed all but 4 items, what you'll be left will be the sketch of the 4 items. So in fact, you can go and retrieve each item as you wanted. And that's what the sketches do. So, it's not something special that we invented, right? This is because these are just linear operations. And so it turns out actually in application this is very powerful. This is useful in a very key way in applications. So anyway, so this tells us that the kind of problems we're dealing with are not easy to solve with just directly sampling. So how can you use the count-min sketch? As I said, you can figure out, it's useful when you want to figure out large items, not the small items. So one way you can do it is find out what is called heavy hitters. Okay? So I don't know who actually first used the word heavy hitter in this context in a paper, but I certainly remember a conversation a long time ago where we came up with heavy hitter because that was a time when baseball was going through difficult times with with the hitting scandals, and so that was on our mind. But heavy hitter is a more natural term. Okay. So, given a array f1 through fn, we can do all the transactions such that if I just anytime people say, tell me who return the heavy hitters. So heavy hitters are those guys who are at least 2 epsilon times f, who are at least 1,000th of the total volume. Then you'll set epsilon to be like 1 in 10,000, and you'll ask what is f1, what is f2, what's f3, and return all the guys who are more than, say, 2 times the estimate you want. Now, once you do that, then you know that you returned all. If you return guys who are at least 2,000, 1 in 2,000 of the total volume, then you surely return all the guys who are at least 1 in 2,000 of the whole volume, because that's our sketch has a property that it's a one-sided error. If somebody was large, it will remain large. But you might return somebody who is not very large, but not many of them. So you will never return anybody who was sort of 1 in 1,000 smaller than the item that you're looking for. Okay? So you have some small amount of error in which you might return. You're looking for items which are at least 1 in 1,000. You'll definitely return all the guys who are more than 1 in 2,000 or 1 in 500. And you'll never return anybody who is less than 1 in 1,000. But you might have a small amount of error in between of items which are between 1 in 500 and 1 in 1,000. Okay? And you can do it by just asking those questions, what is f1, f2, f3, fn? And that already gives you sort of something powerful. Okay? And another observation you can make is that, well, this means that you have to ask query, what is f1, what is f2, what's fn, for each of the values of n, and n could be very large, and that's a long time. It takes a lot of time. So this is called a recovery problem. And we can, in fact, design an algorithm where you can recover even faster than this. Okay? So I'm not going to go through the detail, but the way to think about it is that it is an array, and you're looking for these guys who we call heavy hitters. Okay? Let's say there are k such heavy hitters. Right? If the heavy hitters are 1 in 1,000 of the total volume, that can be no more than 1,000 heavy hitters. So that's the number k. Those are the big guys you're looking for. The algorithm I showed so far said find out what is f1, what's f2, f3, and ask each of the queries, and ask n queries before you find out what the heavy hitters are. A different algorithm would work as follows. You take these n items and you hash them into bucket, let's say 1 over k, say k squared buckets. Okay. So you're looking for k big guys. So take the n items and randomly map them to, say, k squared buckets. Then think about what these particular k big guys will end up doing. Each of them randomly goes to one of the k squared buckets, so the probability that any 2 of them land in a place is very small. Okay? So what that means is that these heavy guys will all get distributed. There will be k squared buckets, and all of these big guys will be in some group by themselves. Okay? Furthermore, if you look at what happens to all the rest of the guys, the contribution of the other guys to any one of these buckets would be the total sum of all the items divided by k squared, because that's the number of buckets. Okay? So here is an item which is like 1 in 1,000. There are 1,000 such items, and we throw it into a million buckets. So that item ends up being alone of all of the other 1,000 items. And everybody else's contribution goes down by a million factors. So this guy becomes very large in that group. Okay? He's more than half of the other guys in volume. Okay? Then you can run a CM sketch on that set and pull out the heavy guys very easily. Okay? In fact, it'll be one guy who can pull out easily. Okay? So this has this property that you'll be able to solve this problem by just throwing into something like k-square buckets and then doing some simple log n type recovery CM sketch there. So something like k-square log n space, you'll solve this problem in that much time, in log time. So you don't have to ask query for each one of the FIs. You'll be able to do it in logarithmic time. This is the main idea, but it can be more technical. You don't have to throw it to k-square buckets. You can do it in something like k log, something linear in k. Okay? So that will still preserve the fact that you will be able to find heavy hitters with space 1 over epsilon log n, rather than 1 over epsilon squared log n. Okay? And these are some of the common techniques in this area. So one technique is to hash so that you get the contribution of the bad guys to be small. Other technique is to hash so that you can spread out the guys you're looking for so that they're alone, and then you can do more careful identification of those guys. Okay. These are some of the techniques that we use when we start using the count min sketch. Okay. This takes order extra login time extra in time and space if you do this fast recovery. And for those people who really care about this, and this I'm sort of putting as a placeholder, this will give you a result that says, if you have a large array, if you have a large array, and you want to find the best k-term representation, I'm jumping over a lot of math here, then we can find one which is as good as the best such representation plus epsilon times some error. Okay? There are tighter forms of this that you can write. Okay? And you can think of this as a compressed sensing result. Okay? In fact, when I heard of initial compressed sensing, and I could reproduce this argument directly from count min sketch. Okay? The original compressed sensing has a few more features that it guarantees, and the algorithm is a little bit more complicated and so on. But this is there are people, Piotr, Indek, and his students did some experiments to show that this method does very good compressed sensing. Okay? So compressed sensing is a very nice, rich, complicated area. I'd encourage you to follow up on the area. But at least the basic result, we can get using this count min sketch. That's always fun. Okay. There is a website that tells you a bunch of other applications of this, and there's been a lot of. I mean, you can use this to do inner products, which is useful. I mean, Alex has explained many nice uses of, many nice extensions of this and uses of this. We can, if you're interested, you can go check out these places. Okay. I don't know if I can believe everything I read in a wiki article, but there was a wiki article that said that, maybe a blog article that's even more unreliable. Yes. A blog that said that count min sketch is in some of the Spark, Storm, or Hummingbird, or one of those Twitter things. So it's a simple data structure to use for a whole bunch of silly problems. So it gets used a lot. And you might, if you want to try this out, it'll be easy for you to find code out there. You don't have to rebuild all the stuff on your own. I want to quickly tell you another primitive that I like that's useful. I'm not sure I have time to describe how it works. I'll give you the main idea. Okay? So this is a tool that I found very useful for my work in streams, and it's a tool that count min sketch, it's a problem that count min sketch does not solve. So you need this other tool in your bag. Okay? And so the way to think about it is that you have, as before, a large array. It's a virtual array. You don't materialize it. And you're seeing updates to the array. And let's also assume that the updates are such that the items are always non-negative. Fi is non-negative. And then the query now is not what is Fi, but it says, can you give me a sample, a distinct sample of the items? Okay? Now, when I say give me a sample, you could just return uniformly any one of the items seen so far, but that's not what I want. I want you to return one of the items uniformly from the different items you've seen so far. Okay? I think there is should be a strictly greater than 0 here. Okay. So in other words, you have a large array in which you're tracking transactions. Some of them are 0, some of them are very large, and some of them are small. What I'd like you to do is just look at the items which are not 0 and return them with equal probability. In other words, if an item was seen 1,000,000 times, if another item was seen once, I don't want you to distinguish between them in the probability at which I get a sample. So it's got a distinct sample in the sense sample among the distinct items. So the fact that some items appears many times as a large volume doesn't affect the random sample. Okay? So in other words, if you had one item which appeared 1,000,000 times and then 1,000,000 other items appeared once, then if you took a uniform random sample, then the item that appeared 1,000,000 times will appear with probability half. But if you took a uniform distinct sample, the item that appeared 1,000,000 times will appear with the same probability 1 in 1,000,000 as another item that appeared only once. Okay? So if we want to get items here with probability proportional to the number of items, universal proportional number of items that appeared at least once. Okay? So replace the greater than equal to by greater than 0. Okay? This is called a distinct sample. Okay? And again, if you want to do this with full space, it's very easy. Maintain a B tree of all the items and then pick one of the random index. Okay? Or if you want to do it with a hash table, maintain all the hash table, and you can try to pick a non-empty hash table quickly. Okay? But like before, we want to do this with very small space. Okay? We want to be able to do this with logarithmic space. Okay? And there is a nice solution that uses 1 over epsilon space. Okay? It's a very cute solution. I don't have time to sort of describe it. And in fact, it works even when you increment and decrement. It's a very nice solution. And I would encourage people to look it up. Okay? And this is something that I don't know how to use count min sketch to do. It is actually returns a sample of an item in the initial data set, even when things are being removed and added and so on. And once you have this, you can solve a whole bunch of problems. Okay? All the problem, things like how many packets were seen only once. All the items about rare items, you can answer those problems, statistics on them, but if you have this data structure. Okay? And as I said, I'm not going to give you a way to do it, but such methods exist. I just want to give you one nice application of this that some authors found recently. Okay? It's for a graph problem. Okay? And I think it's a nice, cute little application, so I'll tell you what it is. They call it graph sketch, which is nice. Okay? So the graph sketch is going to be yeah, I'm not sure. Okay, so let me summarize this this algorithm. Okay, so if you take an algorithms course, undergraduate algorithms course, there's definitely a graph algorithms part, and there'll be some questions like, is the graph connected? Okay? And so you can pick a vertex, look at the edges. Out of it, you can do some search, you can do walks, depth first, breadth first, and you can see what is connected components. And you can even maintain a spanning forests independently. Every time you see an edge, if it happens to be, you maintain certain components that are connected, and you take a new edge. If it happens to be within one component, then it's not useful because it's already connected anyway. If it is between two components, then you collapse the components, and then you maintain this, and that'll give you a set of all connected components. So these are all algorithms that you may have seen in your algorithms class before. Okay? What these authors figured out how to do is, you want to be able to simulate the same. You can simulate the same algorithm as you see edges come in one after another. So what you need to be able to tell is when you have a set of vertices and a cut with the set of vertices and the remaining, you want to be able to get a edge coming out of the set, and you want a random sample of the edges coming out of the set. Okay, and you want to be able to pull that edge out, figure out what component it connects to, merge the two components, and again ask the same question out of the new component, what is an edge coming out of the new component? Okay. So if you think about this repeatedly, what you would ask is to be able to take some two sets, merge them, and ask what's an edge coming out of that set, and pick one with equal probability. Okay. So what they managed to do was run the same algorithm, except that they keep an appropriate sketch on the edges coming out of a set, so that the L0 sample I told you, the distance sample I told you, would be able to give you an edge they want every time. So they'll be able to keep a sketch of these two partitions, merge them, and they'll give you a sketch of the partition, and from there sample one of the elements as an edge, and then continue. Okay? It's a high-level description of the algorithm. It's very nice because it looks like a regular algorithm that you would run if you had a full space data structure, except that whenever you need an edge, you can call this sample algorithm. Okay? And they're able to then use that to estimate the connectivity. Okay? It's a very nice little algorithm. It's from a Soda paper. I hope you have a chance to check it out. So it's quite nice. Okay? So I'm sorry, I'm not going into the detail of the algorithm, but the way to think about it is that you might come up with a problem in your task, maybe machine learning task, whatever, where you have to say something like find the vector which has the smallest distance to this vector, or find the next greedy vector which has the largest projection along one direction. Some task like that, that's the way you write a code. And then one way to employ these algorithms that we're talking about is to take that primitive and be able to replace it quickly by a small space data structure. Okay? And that'll be very nice for you to do. It'll work if it does work, but then you have to figure out how to maintain that sketch as you keep doing it. Okay? And that's also always a tricky part. Okay? And in certain graph problems, these authors found a way to maintain that. It's a nice little thing. Okay. So the sketch I mentioned is not only useful for doing this L0, L1, and heavy hitters. It's also useful for looking at L2 distance between vectors. The same sketch, just that you have a few more extra counters, will give you a good approximation for L2 approximation. And once you have that, you can do least squares approximation. So for me, what was exciting was this least square estimate is a sort of result from Gaussian times. Right? That almost sounds like a pre-dinosaur times. Right? Yeah, I had a joke about this. It didn't go so well once. You know, there's something called a Gauss-Seidel method in numerical analysis. I don't know how many of you know about this. There's a nice elimination method for Gauss-Seidel. And the joke is, who's Seidel? And Seidel was Gauss's programmer. Okay, this was a joke I used once, and it didn't really go well, because I was telling somebody who was called Seidel. Anyway, so Gauss-Seidel, so nearly Gaussian method gives you a least square approximation. So the least square problem says that you're given an n by d matrix and a vector of dimension n, and there's a b vector. And you're asking, look, I'm given a and b, and I want to find the x such that ax minus b is minimized in L2 error. Okay? So I'm given some matrix, and I'm given a column vector, and I want to find the column vector such that ax minus b is minimized in L2 error. And this is like one of the first problems you come up with numerical analysis, right? And the way to do this problem, there's a well-known method that gives you n d squared algorithm. Okay? And we want to say, can you do better than this? Okay? And we managed to get a result which does n d log d, and it was pretty exciting for me when I got it. It was a long time ago. When we got it, it was very exciting. We got that it could improve something like least square approximation. It was pretty exciting. And we went from n d squared to n d log d. But I think now there are sort of this result, David Woodruff and Clark and others, there are now a bunch of things you can do of a similar ilk. Okay? By the way, that original result says all you have to do is compute something like a sketch of A and a sketch of B. And from the sketch, you can solve something like least square approximation on the sketch, and it'll give you an approximation you want. It's very simple, very cute. You want to solve least square approximation, work with the sketches. Okay? And you can get a good approximation to that. Okay? And the sketch is so small in size, so the running time is improved. By the way, you can do similar tricks for now low-rank approximation. There are versions of SVD, versions of decomposition results, and there's a lot known about this. And I think Michael Mahoney has a textbook on, a book on linear algebraic methods, which has a lot of small space methods. Okay. One of the difficulties we had with this result when we had it early on. So I'm telling you the current best result here. There's a long history to get to this result. Okay, when we had this result, I don't know, maybe 2004 or something, it was difficult to publish because people said it was obvious. If you project the matrix, you should be able to run faster. Okay, so it was difficult to convince the people that, well, you can always project something onto something, but you had to have the result should have an accuracy. You should be able to prove something about it. And So we have some difficulties with that. Okay. Yeah. This here is another result that I really like. It's a result by Piotr Indyk and his collaborators at MIT. Very nice set of stuff. Okay. So, the fast Fourier transform for a given signal can be computed in n log n time. It's probably one of the earliest n log n time algorithms. It's a beautiful algorithm, the fast Fourier transform algorithm. Okay. And we don't know any way to improve this algorithm. And for 30 or 40 years, we've been fighting with this question. In fact, it can be tied to really fundamental questions in complexity theory, like, is multiplication harder than addition? Okay, we don't know how to prove that multiplication is harder than addition. In other words, can we do multiplication linear time? We can do addition linear time. Can we do multiplication linear time? And so there is a lot of nice theory context to the fact that we don't know formally how to prove that multiplication is harder than addition in general computational models. And so one of the approaches to multiplication is using fast Fourier transform that gives you the n log n algorithm. So can you improve fast Fourier transform? Okay. And we don't know, but we now know that if fast Fourier transform takes a signal of size n and computes another representation of size n along different dimensions, and to the extent that the new representation has k non-zero elements, means it's sparse, then there's an algorithm that will compute an approximation to that, which is just in k log n time. Okay, that's really beautiful, right? The signal is n in size; it doesn't even read the signal. Okay, if you said that 10 Fourier coefficients are sufficient to get most of the signal representation, this algorithm will work in 10 log n time. Okay? It's a beautiful thing to be able to do. In sublinear time, you can pretty much get a good approximation to the signal by just sampling the right places. Okay? So this is the most recent. I think there have been some follow-up work, but this is I'm stating the most recent work in a long line of work. Okay? So for example, in 2005, we had a result that said you can do it in k raised to the power big O of 1 log n time. There was some constant k raised to 6, 60, 65, 1600, I don't remember. Some large constant, we could do this. Maybe it was 3. But these guys really got it down to the best thing you could ask for, k log n, and maybe k log n over k or something like that, even better. Okay. So it's very nice that we are now able that, we can't improve Fourier transform, this fast Fourier transform per se, but even if the Fourier function was represented in something like n over log squared n, or something even a large number of terms, not like 100, a constant number of terms, but something like n over log squared n, if we still n over log n, we have an improvement to fast Fourier transform. So it's only in the case when the signal is like n over 2 or some sort of signal representation that we don't know how to improve the result. Okay. It's really a big improvement, a really big step for them. And they have extensions of this to 2 dimensions and so on. Okay. So I'm just trying to tell you that I started with something simple like indexing using Countman sketch, and there's a L2 version of this. It's the same kind of sketch. It's the same throwing into heavy hitter bins and iterating. It's the same outline of the algorithm. Okay, you need more technical pieces, but it's the outline of the algorithm you heard so far that gives you these kind of results. Okay, it gives you least square approximation. It gives you fast Fourier transform approximations. And it's pretty cool. You should check out the work if you're interested in this, because I think this is a pretty significant development. There's got to be a good learning joke somewhere, right? I mean, learning theory people must have some sense of humor. There's got to be a good learning joke somewhere. What do you think, Alex? And it's not my community. I can't really joke about them as much as I can joke about Agham's community. Database people, I think I can tell a couple of jokes, I'm sure. The problem is, well, you know how they look like, right? Unfortunately, when I go to stand-up comedy clubs, I go to stand-up comedy clubs sometimes, and it's fun. When I'm in the audience, I can immediately tell what's going to happen, right? Some guy comes up there to tell a joke, and he looks at me, and he immediately thinks of a Dell joke. Because I'm an IT guy from India, right? So there's a Dell guy joke, and it's really interesting. Okay, every stand-up comedy club I've been to, the guys eventually come to a Dell IT guy joke. So there's got to be some signal here.
I mean, the one thing that probably everybody knows is the dot selection paper.
What selection paper?
Called dot set selection. I mean, it was a will select data sets until you find one at which your algorithm excels. And so essentially you can do the equivalent of learning theory bound on how many data sets you're allowed to discard and pick a new one. The algorithm is probably worthless. So just Google nearest data set selection and you'll find
Okay.
there's a nice video.
Hey, you're not allowed to plug products, by the way.
What?
You're not allowed to plug your employers, by the way. I was kidding.
Okay, we can try different services.
I was kidding. So sometimes, one of the hardest things to teach, one of the hardest things to communicate to researchers, it's also the hardest thing to communicate to students when they do homework problems and puzzles, etc. Right? Okay. Which is that the way somebody communicates a problem or a puzzle already gives you a lot of hints, already tells you a lot about the solution. Okay. So, for instance. If you take digits from 0 through 9 and construct all permutations of these digits, you get a whole bunch of numbers. You take digits 0 through 9, permute them, get a whole bunch of numbers. And the question is, how many of them are prime? Okay. That's the question. Okay. Now, when I tell you this question, it looks like something you need to think about, right? There are a very large number of such numbers, and you don't know which of them are prime. And how do you estimate these prime numbers? Okay. But if I told you that I want to give you an answer in 30 seconds, you can give me an answer in 30 seconds. Okay. That should tell you something about the problem. Yes. Now, there are only a few answers possible in the 30 seconds of thinking. It's either all the numbers or none, okay. Or half. Okay. And you can do a little bit of targeted thinking and realize that none of the numbers are prime. They're all divisible by something if you look at it. So it's very useful when I said, just you can get the answer in 30 seconds. Okay. And there's another similar another problem that it got me stuck for a long time. Okay. It says you have numbers. Zico and I play a game. Okay, we have cards numbered 1, 2, 3, 4, up to 9 laid out on the table, and the numbers are visible. Just 1, 2, 3, up to 9. Zico goes first. He picks a number. I go next. I pick a number, and we take turns picking numbers. And whoever gets 3 numbers to add up to 15 wins. Okay. So I see the numbers he picks. And the rest of the numbers are all known, so it's not one of those card games where you flip numbers, etc. All the numbers are laid out, okay, 1 through 9. And we play the game, we see each other's moves. The one who wins, who gets 3 numbers to add up to 15 wins. Okay. And the question is, if Zico goes first, does he have a perfect strategy? Which means no matter what I do, no matter how smart I am, can he win the game? Okay, that's the question. Or do I have a perfect strategy if I go next? But either way. Okay. So the person who gave me this question was an evil person. Okay. So it's I thought of it for some time and I was struggling with it, and then I said I'm going to give you a hint. I said, all right, great. What's the hint? Okay. So the hint is one word. Okay. That was his hint. The hint is one word. That was it. He didn't tell me what the word was. Okay. It was just one word. Yeah. Sorry? No, that's not the answer. The hint cannot be the answer. Hint has to lead you to the answer. The art of giving the hint, to give a hint is already an art, right? So the hint, it's a terrible art. The hint was right. It's one word, okay. And it was a useful hint, okay. But it doesn't. He didn't have to tell me what the word was. And there are many such examples like this. I think Peter Winkler has one in which the answer is also one word. The hint is one word. the hint says the answer comes from one word. And if you think about it, you agree with him after a while. It's true. So anyway, this problem is worth thinking about. Okay. You want to have 3 numbers add up to 15, who gets to win? And if you really want to do this, if you really want to attack the problem, it'll be fun to actually start playing it a little bit by yourself. Then you get a better idea of what happens. Okay. Then you start taking 6, I start taking 4, he takes 3, I take 7. And so you start seeing what you employ if you play it a little bit. I want to tell you 3 or 4 different problems now, and I don't want to solve them. I just want to tell you these problems which I think are large areas of problems that I feel like they're not well formulated, they're not well attacked, and we should be doing more about them. Okay. This is one of the fun things in my life. I like to be able to think of areas where I think we should be doing more effort, and it's a trick to formulate problems. And once you formulate them, the area will come together very nicely. And okay, so I'm going to give you a few examples of this type. Okay. So first topic is roughly distributed learning. Okay. And that's a very broad topic. I'm sure many people in learning think that they do distributed learning because they have multiple machines, and your exercise involves multiple machines. So you're doing distributed learning, but these sort of authors try to sort of think about what's the simplest distributed learning problem on which I need to actually prove a theorem, a bound. And what's really the crux of this problem, right? And I'm calling out both the teams. I think they're both. It was sort of a simultaneous result, but more or less both of them approach the problem in a similar spirit. Okay? The problem is Alice has a data set DA, and Bob has a data set DB, and they want to learn something jointly. Let's say a linear classifier. Okay? And here is the interesting part. They want to communicate as small number of bits as possible. Okay? So the way I showed the lower bound for counting in sketch, you saw that there is a connection between number of bits communicated and the space used by data structure. So if you think about a large data set like this, if you cut it somewhere in between, what goes between these 2 cuts is the data structure that you store. So if you have these 2 parties with these 2 parts of the data, then that has to be related to the communication of the number of bits. So there is some connection. So the problem, the way we want to ask here is that you have 2 people with 2 different data sets, and jointly they're part of one data. Jointly, you want to be able to learn a classifier on the joint set, set of data, right? And what you don't want to do is you don't want to have Alice send the data to Bob, and Bob spends all night learning the classifier, sends the classifier back to Alice, solving problem solved. You don't want to do that. You want to figure out what is the smallest number of bits that can be communicated between Alice and Bob to solve this problem. And it also turns out that you don't want to think of it as a one-shot game. We already know that if Alice had a bit vector and Bob had to know what the bit vector was already quite a lot of bits. So you want to be able to be a little bit more gentle about formulating this problem. Okay. And what they did was they came up with this measure, EDH, which is the if you look at a classifier, look at the number of points misclassified by this classifier, and you want to be approximate in this function. Okay? You want a classifier which will be some approximation of the best classifier. Even the best classifier will misclassify some of the points. So you want a classifier which is some epsilon approximation of the best classifier. And it's not an epsilon multiplicative approximation. It is the number of points misclassified by our algorithm, our classifier G minus the best one, is some epsilon times a set of all points. So notice that again, they give themselves an error which is proportional to the whole total data size. Okay? So they don't want a classifier such that they're not asking for a classifier such that it differs from the best classifier in misclassifying it half the 10 points, so constant number of points, or 1 plus epsilon times the number of points that are not classified. They don't want multiplicative approximations. They're giving themselves a lot of room. They're saying that the points misclassified by my classifier, and if you look at that, how much is it different from the one that's misclassified for the optimal one? Then the difference is at most 1/100 times the set of all points. So if you have 1,000,000 points, they give themselves an approximation that's 1/100 of the 1,000,000 points. Okay. So that's similar in spirit to what we've seen in data streams, right? We gave ourselves an approximation for f tilde I, f of I, which was like epsilon times sum of all f's. Right? So it's a very similar in spirit the way they formulate the problem. And then they showed that there is a log 1 over round two-way communication protocol. Okay, so in streaming we used log 1 over epsilon sort of space, and that here they have only constant number of bits per round, but it's a two-way communication, and the number of rounds is log 1 over epsilon. Okay, so it's an interesting method. You can sort of see that. You don't want to compute the classifier and just send it over. And even if you did, for your points, it's not clear it's a classifier for all the points, right? So you want to sort of send, algorithms will have the property that they sort of start sending classifiers and regions around the classifiers and regions of uncertainty around the classifiers, and they sort of try to zone the region down iteratively until they get a pretty good region around the classifier. Okay? So that's an interesting algorithm. And it may not immediately fit some things that you have in mind, but I sort of feel like there should be more work of this type in this model. So what do more rounds give you? What do fewer rounds with but more bits give you? Okay, these trade-offs are not well understood, and I think that asking this in a systematic way, showing some lower bounds of this kind of type, will actually make it a richer area. Okay. So by the way, notice that nothing in this slide is obvious for me. Okay? When I first started formulating the problem, it's not clear that we should be proving an approximation on the number of misclassified points. Okay, that measure itself is a progress to sort of identify that measure. And then look at the difference between that and give ourselves a room proportional to the total data set size is also something interesting. So there are a lot of decisions being made by these authors in formulating the problem. I think they're good decisions, and I think they're good models to work with. And then the idea that you can have multiple rounds, not just single round, and then there's two-way communication. So what you notice is people trying to get at the problem of how much communication is needed for people to jointly learn a classifier, and sort of trying to see what models can we formulate and what can we prove about them and playing with it. So it's sort of a very early stages of understanding the whole picture there, right? And I think it's a nice problem to attack for some time. Okay. I think I mentioned that big data for me means privacy, and privacy is a hot topic for a lot of people. And, luckily, I can stay on the mathematical side of things. Okay, so for a long time, I'm pitching for differential privacy, and it's a lot of great Microsoft researchers have developed differential privacy to a wonderful area. So I'm sort of pitching that area, but mathematically, I'm very excited. I like this definition. So let me tell you what it is. Okay? So most of you, I don't know if you've taken any classes in privacy or security, etc. Privacy is very hard to define. Okay? 10 or 15 years ago, when I would talk to experts in privacy, they'll tell you privacy is not security. Privacy is not cryptography. Okay? What is privacy? Well, it's something like a policy. It's something, so it's been always difficult to define what privacy is, right? And they'll be like, privacy is whatever you can live with, and it differs from people to people, and it's very nice, but as a mathematician, I can't work with that concept, right? So there have been cryptographers trying to formulate the notion of privacy, and a bunch of attempts at it. And one approach that I really like is the idea of differential privacy. Okay? So notice that if you're very straightforward about formulating privacy, you would say something like, look at the data, and it's held by somebody, and you can ask questions to the data, questions about the data, and no matter what questions you ask, it should not reveal something about a person. Okay? That seems like a way to ask this question, right? And it should not reveal something about a person, or maybe a different way to state it is that if I look at answers to a lot of queries, I shouldn't be able to figure out something about a person. But figure out how much time, how much space. Generally, you would think, well, maybe I should make it polynomial time. Maybe you should say that, well, somebody can break the system if you give them exponential time, but maybe if you can bound them in polynomial time. So this is the way you tend to think about the problem. And it's a little bit messy once you say, what can you do in polynomial time? Well, we don't know what we can do in polynomial time. We don't know the difference between polynomial and exponential in a large sense. So it's hard to make progress of this type. But the way differential privacy people approached it is that they had a very nice, simple definition. Right? They said, okay, the notion of differential privacy says that you have some function that you're computing on n people or n items, okay? And output some value, some function that you computed. Now, the computation is supposed to be differentially private, is defined to be differentially private. If you take that input, and if you change the input a little bit, in one of the items, say the name, salary of one of the users in the data set. Okay? then the output that the algorithm provides, okay, is not very different. Okay? It should still be approximate, so you're trying to compute some function on the data set. You only care about it if what your output is a good approximation to what you want to compute. So that's one aspect. But it's private only if a small perturbation of the data on each individual user's data, something doesn't look different in the output distribution. Okay? That's the way they defined it. Okay? So notice that this is a purely mathematical definition. It doesn't have any notion of privacy defined into it, right? It just says, I'm going to have a function which behaves similarly if the input changes in one bit or one user information with one user. Okay? And those functions are what I consider useful. So now the question is how accurate they are and what is the perturbation of the users it can take, this algorithm. And those are the two parameters. Okay? But what is nice about the definition is it's absolutely, it doesn't matter how much time you take. Okay, so what this argues is that if I take a data set and one of the users decides to give the data or not give the data, from the output of the algorithm, you can't tell the two worlds, no matter how much time you're given. No matter, not polynomial time, exponential time, whatever, no matter what. Okay, so it's not a computational way of defining it, it's a nice way of defining it. And then the argument, they sort of switch around and says that if you had such an algorithm, then why wouldn't a user want to give the data? Because whether they give the data or not, the output function is not going to tell them any unique thing about themselves. So whether they give the data or not, it's going to have the same output, so you might as well give the data. Okay? So it encourages people to give the data and assures them that their data did not make the biggest difference in the outcome of the results. Okay? So the way for example, if you have n people and you want to compute their average salary, then what this method would say is that say compute the average salary, and then add a noise which is quite large compared to any individual person's salary. And now if you return that answer, now whether that person is there or not there, the outcome would not look very different. Okay? If the noise is pretty significant compared to one person's salary, then whether they're not there or not there, the outcome of the noise sort of will swamp out whatever their input would have been. Okay, so that's roughly the way you think about it. So differential private algorithms tend to, when we do it is compute the function and then add a suitable noise. And the noise will depend on the sensitivity of the function to any one of the inputs. Okay? Those are the differential private algorithms. Okay? So that's all background to what I wanted to build out, which is a bunch of authors asked the following question. Look, this differential privacy is very good, but if you had an algorithm that was differentially private, but if someone broke into the system and looked at what you maintain in your system, then you would no longer be private. So for example, think of the algorithm that keeps every person in this room their name and their age. Okay? And then when somebody says, give me an average age or something, it says, computes the average and then adds a noise and returns the answer. That algorithm is differentially private because the output is not sensitive to any one of the inputs. It added the right amount of noise. But if someone were to look into the code and break into the code, they have a linked list, a hash table of all the people's names with the salary, right? With age. So that's not a very good algorithm. So they came up with this notion of pan-privacy, which is privacy even if someone actually breaks into your code and looks at your memory. Okay? And what was interesting, so and they defined it in a beautiful way. They said that no matter if if two data sets are so similar to each other, or the internal states are similar to each other, you want the output to be indifferent. And notice that this notion of pan-privacy says it doesn't give any limitation on time or space of the algorithm. It says an algorithm is pan-private if it has a property that you look at the input, and if an input differs a little bit, or if somebody broke in and looked at the internal state that differed a little bit, the output distribution should be the same. Okay? So for example, you could take a data set of n people and store an exponential size data structure. Hide the people's identity in the exponential data structure and compute an answer and return it. And if it has a property that it is differential private, you are pan-private. Okay? So that was the way they defined it. And what we could show was that we can basically get pan-private algorithms for a lot of problems using count-bin sketch variation and L0 sample variation. Okay? So in other words, if you want to protect yourself against break-ins, you automatically end up storing small amount of data, small sketch data set, in order to implement these algorithms. Okay? Which was very surprising for us because the initial definition doesn't require you to use small amount of space. You can use any amount of space, but we can use count-bin sketch to solve some of these problems and be pan-private, which was another connection that was interesting for us. Okay? So if you're interested, take a look at this paper. There have been a few more extensions of this since then. Okay. By the way, there's a reason why I'm telling you these problems. They sound like they're maybe from left field. They're not. I would like to see what private machine learning is. And I would like to see what kind of properties of machine learning we can do that preserves any notion of privacy or extensions of the privacy. And I believe that when you start getting into sort of the efficient methods for some of these problems, you'll end up using a small space data structure like sketches. Okay, this is what I believe would happen. But before you do that, you have to formulate the problems the right way. And I'm sort of giving you pointers on where people have been successful in formulating simple problems, simpler than the kind of ones that you guys think about. Okay? And I hope that that gives you an idea. I want to talk about. Okay, so let me tell you a couple of other problems which are not on the slides. Okay. So here is a problem I've been working on recently that I really think that more can be done. Okay, this involves mechanism design and pricing. So imagine that there are n people in this room, and each of them has some feature set, where they're born, their age, their height, their Facebook updates, their browsing habits, whatever, because they're a feature vector. And you're trying to figure out some classifier, and they are sort of 0, 1, and each of them knows the 0 or 1. Okay. Now, if I ask you guys to give all your data, then I can learn some classifier. I can run some machine learning code and learn whatever I wanted. Okay. But suppose you guys are really smart about it. You'll say, look, I'm not going to give you my data unless you gave me $10. Or I'm not going to give you my data unless you give me $1 million. So each of you is allowed to say how much money you want to reveal your data. Okay, that's the model okay. So now therefore you have n feature vectors, each of them with the tagged output of the classifier, and each of them is an individual who strategically says how much they need to be paid to reveal the data. Okay. Now I am trying to run some sort of experimental design case. I want to learn the classifier, but if I had all the money in the world, I'll give everybody whatever money they ask for, right? But let's assume I have a limited amount of money. Okay. So now the question is, which people should I pick, and how much money should I give such that I will get a good approximation of the classifier I want to learn? Okay. So it's a mechanism design question in the sense that I want to set up the mechanism such that people who, if you really value your data as $10, you should be able to get paid $10. If you value it as $100, you should be able to get paid $100. Okay? So the mechanism should have some sort of true value of each user. I should set up the rule such that you get your value. At the same time, I get to learn the classifier one with the best thing I can do with the given budget I have. Okay? So it's not just an optimization problem of pick a subset of people and the money and find the best solution, because if you know I'm going to do that, each of you will declare to be $1 million worth, right? If you know I have $1 million, you'll say $1 million, right? So there is no actual truthfulness to the amount of price that you put down if you don't have a good mechanism design. Okay? So this problem is falls in the category of budget feasible mechanism design. Aaron Singer at Harvard has done some very nice work on this when he was a graduate student at Berkeley, and he designed budget feasible mechanisms for large kind of problems. I'm giving you a version of the problem which is what I call experimental design, and people have looked at how to extend this to machine learning tasks, and a lot of people are thinking about this problem. Okay. Now I would like to have more work on this direction, so I hope you have a chance to think about this. Okay, we have a paper. It's on my webpage. We have a paper on this in Leiden conference on experimental design, budget feasible mechanism for experimental design. Okay, I would encourage you to look at that. Another area that's not well understood is a continuous learning kind of area. Okay, so here the simplest problem I would think about will be, imagine that there are n sensors, each of which is measuring something. And they can all talk to a central sensor, and the central sensor should be able to say something like, so let's say each of the sensors is seeing some number of people, and the central sensor says, if the total number of people seen is more than 1,000, I want to have an alarm. Okay, so this is some sort of trigger condition that sets an alarm from the central sensor. Okay, so each of the sensors senses something, and they're allowed to communicate to the central sensor. And the central sensor is supposed to alarm when some condition is satisfied. Okay. And what you count, and this is very interesting, is the total number of bits sent from the sensors to central sensor. Okay. So if you think of a simpler problem where each of the end sensors have some data set, and you want to ask, what should they send so the central data set has some rule that figures out some functional rule, that'll be a one-shot communication. You can figure out what the smallest number of bits transferred. Okay? You can even solve the problem by saying it doesn't have to be one shot. They can go back and forth and communicate as much as possible, but each of them has a static set. That'll be the kind of distributed learning problem that I mentioned. Okay? So one problem says, one shot, everybody communicates central server. What can they communicate? That's what the standard communication theory studies. Another problem says they have a fixed data set. Each of them has a fixed data set. They have to communicate a central server to learn a classifier, to learn a threshold, whatever. And that's a distributed learning problem. They can go in multiple rounds. But I'm telling you a new version of the problem where there are end sensors with data sets, but they're not fixed data sets. They continue to see items as they go along. And at every moment, in the union of data sets seen so far, you want to maintain a classifier. Okay? So obviously, every time you see a new item, if you send it to the central server can calculate everything at once. But that'll be too much communication. Okay? You want to see continuously over the whole evolution of the data, what's the smallest amount of bits I need to communicate to maintain the classifier, maintain the threshold of the central server. Okay? This is a very nice set of problem. This is a very nice set of problem. For example, even the simplest problem of sort of saying each of the end sensors sees some items, and the central sensor only wants to know how many different items that they're seeing altogether. Okay? And that problem has a very unusual and non-standard solution. Okay? In that problem, you would think that every sensor has to send at least one bit for central servers to be approximately right. It turns out that you can send much fewer bits than the number of different sensors. Okay, so the k sensors, and you send bits much less than k in order to get the central server to, with pretty good accuracy, tell you how many items are seen altogether. Okay? Randomization helps a lot. Okay? So this is to tell you that even simple problems have a non-trivial bound, and then we're asking much more complicated problems like how do you learn a classifier and so on at center, and there's very little theory developed around this. Okay? This is what I think of as continuous communication complexity or continual communication complexity. There's very little known about this, and more theories can help us. Okay? So what I'm trying to point out too is that we start with something very simple, like for simple problems, what's the smallest amount of bits you store to index, then heavy hitters. That means you can do compressed sensing, least square approximation. You can try to do fast Fourier transform. Now you say, well, how do I do it if you had distributed machines and minimize the communication? Well, how do you do it if you want to minimize communication, learn particular tasks like classifiers, and how do you do it if the data keeps coming in continuously? Okay. In all of these cases, as you can see, the crux is some small space representation that can be updated. Okay, and I like this way of developing the theory out, and if the richer we can make it, the better it'll be. Okay, that's really what I wanted to say. Okay. I think I'm going to stop there. Okay, that's it. I'm going to stop there, guys. Thank you. I know I'm trying to figure out. Thank you.